In this fifth video of the organic chemistry series, we will be discussing the reactions of basic hydrocarbons, including the alkanes, alkenes, alkynes, and our aromatic compounds. Now, we will not be able to cover all of the types of reactions, but we will cover the most basic fundamental reactions that you would run across. And if you have the foundation of these reactions down, it will not be difficult to move on to specialized reactions in a specific organic chemistry unit or class. Beginning with alkanes. Alkanes are relatively inert and do not react with most acids or bases or any oxidizing or reducing agents. However, they do react with some reagents such as oxygen and our halogens. Remember, our halogens are those elements from group 17 on the periodic table, and they include the elements such as fluorine, chlorine, bromine, and iodine. Now, most of these reactions will be exothermic in nature, and most of these reactions will be as a substitution reaction. This first reaction that I want to go over with you is called a combustion reaction. Now, combustion reactions can happen with alkanes, alkenes, or alkynes. And the way you recognize a combustion reaction is you have a hydrocarbon, a chemical made up of hydrogen and carbon only. It does not matter the size, but you have a hydrocarbon plus oxygen. And anytime we have a hydrocarbon plus oxygen, it will always make CO2 and water. Now, it's exothermic in nature, so it releases heat. Be sure that you can recognize a combustion reaction. You would be surprised at how many students miss this simple equation. Now, the most common reaction of alkanes is a substitution reactions. So alkanes typically will react with halogens when one or more atoms of the halogen are substituted for a hydrogen. And so here we have our halogens. Now, remember that halogens are diatomic, meaning they occur in pairs. And so when we see that occurring in pairs, it's really like having a Cl, Cl. And so what is going to happen is that one of these Cl's is going to trade places with one of our hydrogens. And as they trade places, and on this particular one, I traded it up here at the top, you'll notice that we came up with a CH3Cl, and our byproduct of that would be plus HCl. Now, many of our organic compounds do not show the side product. Each of these reactions on this page represents a substitution reaction. Now, here we have a chlorine, again diatomic, and that's a Cl attached to a Cl. One of the Cl's will trade places with one of the hydrogens, so we'll still have our C2H5 instead of 6, Cl. That hydrogen has moved over and combined with the Cl to make HCl. Here we have chloroethane, and on this particular reaction, what's going to happen is that one of these hydrogens will trade places and will join with a chlorine, and then the other chlorine will attach. And so each one of these, if you will go through and study, is an example of a substitution reaction. I have used chlorine as the reactant. However, bromine, iodine, or fluorine could easily be substituted in its place. Now, the most common reaction of the alkanes was the substitution reaction that we just covered. But when we prepare alkenes, the most common reaction is going to be an addition reaction. So in an addition reaction, the reagent is going to be added to the carbons and the double bond is going to be broken. And that's going to give room for that reagent to come in and attach to the carbons. And so here we have some examples of addition of halogens. And so our X is going to represent one of our halogens, and it doesn't matter which one. But what happens is our double bond right here will break. Now when that bond breaks, we will go to C, C, and you'll notice that we have a single bond, and then we're going to have our hydrogens. But you'll notice that we have an opening here and here, and that's because that multiple bond broke. And that's where our halogens will come in and attach. On this bottom one, we have the ethylene, and when we have the ethylene plus our chlorine, again diatomic, our multiple bond will break. You'll notice that we kept the hydrogens, but because the bond broke, we now have an opening on each carbon, and that's going to be where each of the chlorines come in and attach. Here are a few additional examples going over our addition reactions, and you'll notice that in each case the double bond is broken and that our halogens attach to those open spaces. Many times in an organic reaction, instead of writing this chemical plus Br2, it's going to have the Br2 written on top of the yield symbol. Same thing here. Many times it'll have the reactant written above the yield symbol. Now another type of reaction we can see when we form an alkene is when we take an alkane and we crack it. And cracking is where we take an alkane, a chemical with single bonds, and we break it through heat and pressure to make hydrogen gas and an alkene. And so here we would have our C3H8, and I'm just going to represent those hydrogens with the lines, and we're going to go through heat, and what happens is we're going to make a double bond, so we lose some of those hydrogens, and they're released in the form of gas. Now the combustion reaction is going to be the exact same thing that we saw with the alkanes. We'll have a hydrocarbon plus oxygen yields CO2 plus water. Now on this series of reactions, we've got our alkene plus hydrogen, and hydrogen's diatomic, so it's H2, and then below the yield symbol we have our catalyst, nickel and platinum. Remember, a catalyst starts a chemical reaction but is not part of the reaction. Now these reactions look very similar to addition reactions, but because we're adding hydrogen, this is called a hydrogenation reaction, and this is where we're going to add hydrogen across the carbon-carbon double bonds. So the same thing happens as what happens with an addition reaction. Our double bonds will break, and instead of having a halogen come in and attach, we will have these hydrogens come in and attach. So it's taking an alkene, and by adding hydrogen, it makes it an alkane. We can also have the addition of water to alkenes. Now when we add water, I do want you to remember that water can be written as HOH, where the hydrogen is our cation with a positive 1 charge, and our OH is our anion with a negative 1 charge. And so when our multiple bond is broken, our hydrogen will go to one carbon, and our OH will go to the other carbon. And so we can see that played out. Our bond is broken, and that open area, one will take a hydrogen and one will take the hydroxide. Here we have one additional example where we have water being added to an alkene, where our multiple bond is broken. Our hydrogen will add to one of the carbons, our hydroxide will add to the other carbon. And then what we notice here is that we get this OH compound. And what we have made is we've made an alcohol. And so we'll be talking about alcohols in our upcoming videos, and then how to recognize that it's an alcohol and the nomenclature of alcohols. Another reaction dealing with our alkenes is a dehydration of an alcohol. And alcohols can be dehydrated or have the water removed by heating them with a strong acid. And when you do this, this forms an alkene. And so what will happen here is that as we heat this up, and so I should really have that heat symbol, our OH is going to break away, and one of our hydrogens will break away. And so that gives us an HOH, which would then become our water. And as a result, that's going to leave an opening for us to make a multiple bond right here. And so we make this new chemical compound. Now here, with regards to our alkynes, we can also have an addition reaction. Now with our addition reaction, what we have is we have an alkyne with our triple bond, and typically we're going to have this written out as excess, and then we'll have our halogen. And so when we have excess, that means that both of these bonds will be broken, and so we will keep our original hydrogens. Our carbons go to single bonds, and then because we have excess chlorine, or it may say 2 moles of chlorine, what that's going to indicate is that we will have 4 chlorines, and they will attach to the carbons so that our carbons are bonded in 4 places. Now in this example, it shows us taking our HCl, and it shows us adding, breaking one bond and adding the chlorine and the hydrogen, and then it has plus HCl, and it has the double bond right here being broken, and it adds the chlorine and the hydrogen. So you can show it as a series of steps, or you can write it down as excess or 2 moles and show it as one step. Now substitution reactions can occur with benzene as well. And benzene reacts mainly by substitution reactions. Remember that benzene is C6H5, and so even though we do not draw the hydrogens, we do have a hydrogen attached to each of the carbons. And what happens with our substitution is, again, here we have a Cl attached to a Cl. The bond breaks, and one of the chlorines trades places with one of the hydrogens. And as a result, we would have an HCl, and then we would have that chlorine attaching to where the hydrogen was. Right here, the iron 3 chloride is a catalyst, and it helps to start the reaction. On this page, we have some additional substitution reactions. If bromine is added, it's called a bromination. If chlorine is added, it's called a chlorination. With an NO2, it's a nitration. If we had a SO3 added, it's a sulfonation. So they're all substitution reactions, and they work just like our previous slide. The last type of reaction that I want to cover with you is called a friedelcrafts reaction, and it's a super common reaction that's covered in both general chemistry and organic chemistry classes. And this is a reaction where we're going to take a chain structure and we're going to attach that to a benzene ring. And the way this happens is, again, remember that this is a C6H5, and one of these hydrogens right here is going to break off, and it's going to come over and it's going to bond up with our anion, our negatively charged component in this compound. And in that case, it's bromine. So our hydrogen and our bromine come over and they make HBr. Now what that does is that leaves an opening on that carbon, because that carbon is now a H3CH2, and right there is an opening. And that opening right there is going to come right around, and it's going to attach to that carbon. And so we would have a benzene ring with an ethyl group attached to it. And this is called a friedelcrafts reaction.